Hello everyone. So today what we're going to do is we're going to discuss beginning of chapter 3, which is the definition of the mole, and when we start stoichiometry. And this is the topic, this is the chapter along with chapter 4 where there's lots and lots of calculations and conversions, and it's usually considered one of the more difficult things, especially if you haven't had a lot of chemistry in high school where you've done some of this. So it's going to seem for some of you like it moves pretty fast, and we'll just have to do lots of examples and work through them and make sure to get help by posting to the discussion groups. So the first thing we need to do is start with our definition of the atomic mass unit. So one atomic mass unit is, and I believe that we actually talked about this before, one atomic mass unit is 1/12 the mass of a carbon-12 isotope. And that's how it's defined. And that's how the masses on the periodic table are all set based off of the carbon-12 isotope. And so the AMU, rewrite that a little bigger and better so you can see it on the video. The AMU then is also called a Dalton. People use that interchangeably, atomic mass unit or a Dalton. And the truth is, we really only use this in this chapter. So once we, get going on grams and moles and everything in this chapter, we won't really talk about AMUs again, probably for the rest of the year. It's just this chapter, and it's just a definition that we need to start with. So that AMU being 1/12 the mass of carbon-12 isotope of, one atom of that. The AMU in grams looks like this, and it's 1.66054 times 10 to the minus 24th grams. And that's not a very useful number for us because we just don't have a way of conceptualizing 10 to the minus 24th. When numbers start to get really abstract for us, then things get a little bit more challenging for most people in terms of doing math with them, right? We're used to integers and numbers that we've got some sense of the scale of them. And so that's what an atomic mass unit weighs, that gram, that number of grams. And we're just going to start with an example and try and use this a little bit. And the example that I'm doing is to kind of make a point about why chemists do things the way they do in terms of stoichiometry. So let's pretend we're going to do a reaction. And reactions really are actually mostly in chapter 4, but so we won't be worrying about how to write and balance this right now. But let's burn some coal in air to produce some energy, okay? And so coal is carbon. So we've got an atom of carbon plus a molecule of oxygen gas, and we're just going to burn it to carbon dioxide. So this is really, in a later chapter, we'll even learn how much energy we can get from a reaction like that. And that's one of the things chemists would be interested in doing. So could be an important reaction. So when we do reactions and study reactions in your body, we want to be able to measure those reactions. So let's write that out. Want to be able to measure something about this reaction. How much energy we get from it, how much mass is consumed, how much of something is produced if we're going to make a product, for instance. And so we're going to do this reaction, and I'm going to start here with a little table. And on that table, we're going to do the mass in atomic mass units in the middle. And we're going to have number of carbon atoms. Because after all, what this reaction means is that one carbon atom reacts with one molecule of oxygen to produce one molecule of carbon dioxide. So let's say we run this reaction. One carbon atom. And based on looking at our periodic table, so you can look at the book, find the periodic table, and you'll see that because there's other isotopes of carbon, that the average mass of a carbon atom is 12.01 atomic mass units. And then if you use our conversion of 1 AMU is 1.66054 times 10 to the minus 24th, you can do this multiplication. Do this on your calculator, do the conversion. I'm not going to do it here because it's going to mess up the display, right? Normally I would work this out, but well, what the heck. You won't be able to see it in the Pencast, but you can see it on here, right? So we've got our 12.01 AMU, and then we have 1.66 times 10 to the minus 24th. That's grams per AMU, so the AMU will cancel. So let's do that, times 1.66054 e to the minus 24. And I get 1.99 times 10 to the minus 23rd, it looks like. My eyes aren't that good. So let's write that down. Mass in grams. Okay. Now, here's the deal. We can't even fathom that small of a number of grams, and we don't have a balance, certainly, that can measure that small of grams, even if we had a tweezer that was small enough to grab one carbon atom. So let's think of a big number, okay? Let's take 1,000 carbon atoms. I think 1,000 is a big number, right? If I had 1,000 tomatoes right now, I would be home canning tomatoes. If I had $1,000, I'd be pretty happy. I'd probably go buy a new laptop so that I could speed things up at home for my family. So 1,000's a decent sized number, okay? And if I take my 1,000 carbon atoms times 12.01 AMU per atom, I'm going to get that many AMU, right? 12,000 AMU basically. And then the mass in grams, well, we don't need the calculator anymore, do we? We can just do the exponents. 1,000 times that, now we're at minus 20th grams. But in terms of measuring something, even though that's a big number, we haven't really gotten anywhere, have we? 10 to the minus 20th is still outside of our comprehension and way outside of our ability to measure it. So let's get bigger. What about 1,000,000? 1,000,000's about the biggest number I can imagine. Imagine trying to count to 1,000,000 and how long it would take you. It's a big number. If somebody gave me $1 million, I wouldn't know what to do with it, right? So, yeah, I would. Anyway, how many AMU would that be? We'll take 10 to the 6 times that, and we're going to get 1.2 times 10 to the 7th, right? So we're starting to get these big, awkward numbers. And that's a pretty big number. But let's do that in grams. 1.99, now it's times 10 to the minus 17th, right? Because we just did 3 more exponents. And it just doesn't seem like we're getting anywhere. 10 to the minus 17th is still a number that's way too small to measure. And I don't have as much space on here, but the best a balance can do is plus or minus 0.0001 grams. on a typical, really, really expensive couple $1,000 balance. That's the best we can do. Well, let's really get big. Let's do a million. Not, this is way more than a billion, right? So a million, 10 to the 12th. Huge number. That would be 1.2. Now we've got another, so that'd be 10 to the 13th, right? We add 6 to the exponents. And now, we're at 1.99 times 10 to the minus 11th grams. We're still nowhere near, because this is out 4 decimal places. This is 10 to the minus 11th. So we're nowhere near, even though we have a million, we're nowhere near being able to measure this in the lab. And so what we have to do is invent a number for convenience. And I don't know if you've heard it said that way before, but when we come up with the mole, that's what it is. And they've actually recently, they changed the definition of the mole very recently, within the last couple of years, to make it just a pure number, which I think is a smart thing to do. And here's that number. So 6.02 times 10 to the 23rd carbon atoms, right? We don't care about the mass in AMU anymore, doesn't matter. And that number of atoms will weigh 12.01 grams. Okay, so that's a number that we pick for our convenience called Avogadro's number. And again, Avogadro's number is just a number that we chose so that it would come out this way. So 6.02 times 10 to the 23rd particles. Anything that you're talking about, whether it's atoms or molecules or whatever, eggs, that is defined as 1 mole of whatever it is. So that's our definition of a mole. And the abbreviation for mole is MOL. So I never use it, because what's the point? I'm gaining 1 letter, big whoop. So I just always write out mole, but MOL is also mole. Okay, so let's do some more. We're going to do some more calculations just to get an idea of how big that number is. But first, I want to stress something. So I'll put a lot of stars by it. This is absolutely critical. So the mass on the periodic table is chosen, or the Avogadro's number is chosen so that the mass on the periodic table is the average mass of 1 atom in atomic mass units, but it's also at the same time, simultaneously, the mass of 1 mole of atoms. In grams. And this is really, really important for this chapter. Part of it is we just have to accept what a mole is and start thinking and working in moles by the end of this chapter. but it's just a number chosen for our convenience so that when we look at the periodic table, we can say that 1 mole of carbon is equal to 12.01 grams of carbon, and use that to do our stoichiometry. We can also look at the periodic table and say 1 atom of carbon is the same amount as 12.01 AMU of carbon, right? It means both of those things simultaneously, and we just pick a number, the 6.02 times 10 to the 23rd, so that those things will be true, okay? And we define that as a mole. Now, I'm supposed to, when we meet in person, this is when I would tell my really, really lame mole jokes. I don't think they work over this, but I don't know. What what do you get if you have Avogadro's number of avocados? Well, of course you get guacamole. And there's another one that's way better than that, but I don't think I can do it not in this format. So anyway, what we need to be able to do then, and this is on the study guide for the chapter, but I thought I would write this so that you see kind of where those study guide items come from. So we'll need to be able to convert between grams and moles. So grams, moles, and number of atoms. And then or molecules too. So that item's on the study guide for chapter 3, and it's just kind of showing you where this comes from these definitions, and that's where I get the items on the study guide. All right, and we'll do examples of these just using those conversion factors, but mostly I don't really believe that these conversions are harder than the conversions we just did in chapter 1, where you have to convert, miles to kilometers or something like that. The reason they're harder is we have to get familiar with the terms, right? So why are they harder? I'm going to write this down. I don't usually, but since we're not in person, why are they harder? Unfamiliar terms. So accepting what a mole is and remembering what a mole is and everything else. And the other thing is awkward numbers, right? Awkward numbers. So when we see 10 to the minus 17th and things like that, or even 10 to the minus 3rd and 10 to the minus 5th, it just makes things a little bit harder, even though it's exactly the same. So that's what usually in chemistry kind of trips people up, is just getting used to the terms, accepting the terms and definitions, and not thinking there's anything more to really understand about what a mole is. It's just a number, right, for our convenience. Okay, I just want to then also do an exercise. How are we at time here? Almost 20 minutes. Just want to do an exercise to kind of get an idea of how big this number is. So, line across there. How big is this number that we can't really understand? 6.02 times 10 to the 23rd, or at least I can't understand it. Maybe you can. How big is Avogadro's number? So let's say we take Avogadro's number of pennies and divide them up amongst the entire population of the Earth. Okay, so we have 6.02 times 10 to the 23rd pennies. And we could split that, figure that out. So there's 100 pennies in $1, so that's a huge number of dollars, right? 10 to the 21st number of dollars. And would you take that deal? Would you split that up amongst, if you had that, would you split it up with everyone on Earth? So Earth's population is 7.4 billion. So let's try it. So 6.02 times 10 to the 21st dollars. And let's divide it by, well, last time I checked, 7.4 billion. I'm sure it's gone up a little bit since then. 7.4 times 10 to the 9th. And if you do this, let's see if we can get it to work on a calculator. Do it live like I would. 6.02 second E, because we need practice with that, to the 21st, divided by 7.4 second E to the 9th. Look at that, 8.14 times 10 to the 11th. .14 times 10 to the 11th. So how much money is that? Well, 10 to the 9th is a billion, right? So that means we have 814 billion dollars each. Yeah, I would take that deal. So that just kind of shows you how big Avogadro's number is. So that's Avogadro's number of pennies. And here's the thing, we play around with Avogadro's number of atoms all the time. It's just a scoop in the lab, right? And so you're working with these incredible and not large amounts of things. And we need ways of counting those atoms so that we can do the stoichiometry and the balance when we do reactions. And that's all the mole is allowing us to do. Another thing that I find kind of fascinating as we live out in the country and stare up at the sky with the kids, we had them out and saw our first shooting stars this summer. That was kind of neat. There's more atoms in your body than there are stars in the universe. That's pretty cool. All right, so in the next content video, I will actually have some examples and calculations and things, but that's our introduction to the mole. Maybe I will do it. If you made it this far, you've earned it. So what do you have? I'm not going to write it out, but what do you have? So you only, if you watch it, you'll only get this if you actually watch it. You won't see it if you just look at the printout. What do you see if you see a mole of moles? So you know the little fuzzy little animals that dig up your yard. So you see a mole of moles digging a mole of holes. All right, now did you hear that? What would you see if you see a mole of moles digging a mole of holes? Well, you would see a mole of molasses. Anyway, I kind of like that one. Hopefully you did too. Let me know if you have any questions by posting to the discussion page on D2L. Thank you.